In this video, we will go over what type of stars can go supernova, as well as what is happening internally within the star as it goes supernova. A star holds its shape because the force of gravity inwards is balanced out by the radiation pressure from fusion. Fusion occurs when high-energy particles collide to give off energy, as they fuse. As the mass of the atoms increases due to fusion, more energy is required for them to fuse, and over time the energy decreases. As the energy given off by fusion decreases, so does the pressure that is given off by the fusion, and eventually the resultant force acting on the star is inwards, as gravity is larger, and it collapses. If a star can cause fusion all the way up to iron, it is called a red supergiant. When these collapse, they go supernova. This occurs once the iron core reaches a certain size and collapses in on itself, followed by the outer layers, which creates a bounce back, sending the contents of the star exploding into the universe.
One of the concepts we need to know in order to understand how a star goes through a supernova is electron degeneracy pressure. Up to this point in a star's life, the forces acting on it have been gravity acting inwards and radiation pressure from fusion acting outwards. Now there's no more hydrogen for fusion, there's no more radiation pressure acting outwards. The star still has mass though, and so gravity is still acting, pushing inwards, causing the particles within the star to become closer. The Pauli exclusion principle states that no two fermions can occupy the same quantum state. Electrons are fermions, and they exist in different quantum energy levels and have different quantum spins. So you can have an electron of each spin in each energy level, which means that as the matter is more compressed due to gravity, there is an outward pressure as the electrons will be more likely to occupy the same energy states. So why does this pressure increase as the gas is more compressed? If you consider now electrons in terms of their wave functions, and consider the simple example of an electron in a box with size length A. The wave function for the electron is psi n equals sine n pi over a x, which has kinetic energy minus h bar over 2m d2 psi by dx squared. So if we get the second derivative of our wave function, this gives kinetic energy equals minus h bar n squared pi squared over 2m 1 over a squared sine n pi over a x. So as a decreases, like when the gas is being compressed, the kinetic energy of the electrons increases by a factor of a squared. If we now consider the equation that relates momentum and kinetic energy equals momentum squared over twice the mass of the electron. As the kinetic energy is increasing as the gas is getting compressed, the momentum and thus velocity of the electrons is also increasing. Pressure is defined as force per unit area, and force is the rate of change of momentum. So during the compression, the rate of change of momentum increases, whilst the area decreases, and so pressure increases. This pressure is the electron degeneracy pressure, and it acts in the opposite direction to gravity. When the gas gets so close together due to gravity, we reach a limit as the electrons are reaching speeds near to the speed of light.
This is known as Chandrasekhar's limit, the maximum mass of a stable white dwarf star. The currently accepted value of the limit is approximately 1.44 times of the solar mass. White dwarfs follow the mass-radius relation, where as the mass increases, the radius of the dwarfs decreases. Once exceeding this limit, the white dwarf causes a supernova and collapses into a neutron star or a black hole. This is dependent on the nuclear composition of the star, or the electrostatic interactions between the electrons and the nuclei in the star. An example of an exception was a supernova that was observed in the year 2003, where astronomers believed that it was caused by a white dwarf that was spinning at a high speed and had high centrifugal tendency, which allowed the degeneracy pressure to stabilize the immense gravitational pressure a little more. This allows the mass of the star to exceed the limit. With the electron degeneracy pressure, where electrons gain energy due to the Pauli exclusion principle, electrons can have speeds that reach relativistic speeds, or speeds that are close to the speed of light. This causes the gravity of the star to be unable to support the immense pressure. At this point, matter is compressed until the electrons and nuclei are squeezed together to form neutrons and neutrinos. This process causes the star to shrink and will soon then explode and create a huge blast.
So how does the actual blast occur, and what is the end life of a star? If the white dwarf exceeds the Chandrasekhar limits, the core will collapse until the density reaches that of an atomic nucleus. Now, the strong nuclear force comes into play, creating the neutron degeneracy pressure that repulses the collapse and goes to a halt. The lighter infalling gas around the core will experience a head-on collision and bounce back at very high velocity due to the collision with the halted heavier core. This can be demonstrated by dropping a heavier basketball, which represents the core, with a lighter tennis ball on top of it, representing the outer gas. It is the bounce back of the gas that creates a huge shock wave, or that we call a supernova. Meanwhile, the core proceeds to either a neutron star or a black hole. This is determined by the mass of the core. Those below 2 to 3 solar masses forms in neutron stars, and for masses bigger than this, gravitational force overcomes the neutron degeneracy pressure, and the core further collapses into a black hole.